Alright, let's go. Number 10. The Bion monkey deaths. On December 24, 1996, two rhesus monkeys named Multik and Lapik launched from Plesetsk Cosmodrome aboard Kosmos 22209, a Russian biosatellite designed to study how spaceflight affects primate physiology. The mission was a collaboration between Russia's Institute of Biomedical Problems, NASA, and the French Space Agency. For 14 days, the monkeys orbited Earth, subjected to weightlessness, cosmic radiation, and the psychological stress of confinement in restraint chairs. They were proxies for human astronauts, their bodies yielding data that would inform our understanding of long-duration spaceflight to Mars and beyond. On January 7, 1997, the capsule began its fiery descent through the atmosphere. Multek died during re-entry, his heart failing under the combined stress of sustained weightlessness and the crushing deceleration forces of return. Lapik survived the landing, but within 12 hours, he too was dead. The necropsies revealed a physiological catastrophe. Both animals had suffered severe muscle atrophy, their bodies literally consuming themselves in the absence of gravity. Bone density had plummeted, even in just 2 weeks. Most disturbing were the cardiovascular findings. Heart muscle damage consistent with extreme trauma, evidence of arrhythmias, and stress-induced deterioration that suggested their bodies had been pushed beyond survivable limits. What makes the Bion 11 mission particularly unsettling is what it revealed about our own vulnerability. These weren't elderly, weak subjects. They were healthy adult primates whose physiology closely mirrors our own. If 14 days in space could inflict such catastrophic damage that both died, what does that mean for astronauts spending 6 months traveling to Mars? We continue launching humans on ever longer missions, but the monkeys who went before them didn't return to tell us whether survival is truly possible or merely temporary. Number 9. The Long Duration Exposure Facility. In April 1984, Space Shuttle Challenger deployed a school bus-sized satellite into orbit 300 miles above Earth. The Long Duration Exposure Facility, or LDEF, was designed as a passive experiment, a flying laboratory covered with trays of different materials, coatings, and components. Scientists wanted to understand how the space environment affected everything from thermal blankets to computer chips. The plan was simple: leave it in orbit for 1 year, retrieve it, and analyze what had changed. But the Challenger disaster in 1986 grounded the shuttle fleet, and LDEF remained in orbit for nearly 6 years. When Space Shuttle Columbia finally retrieved the platform in January 1990, scientists discovered something that fundamentally changed our understanding of orbital space. The satellite's exterior was covered with over 34,000 impact craters. Some were microscopic pits. Others had punched completely through metal surfaces. The impacts came from micrometeorites and orbital debris, tiny fragments traveling at velocities up to 50,000 miles per hour. At those speeds, even a paint fleck carries the kinetic energy of a bullet. The discovery was alarming because the impact rate exceeded predictions by factors of 10 to 100. For certain size ranges. The models had been catastrophically wrong. Chemical analysis revealed that many impactors weren't natural meteoroids, but human-made debris. Paint chips from spacecraft, aluminum oxide particles from solid rocket motors, fragments from satellite collisions and explosions. We had filled our own orbital space with shrapnel, and LDEF was the proof. The findings forced a complete redesign of spacecraft shielding and changed how we calculate long-term survivability for space stations. What LDEF revealed wasn't a distant cosmic threat, but a minefield of our own creation, growing denser with every launch, every explosion, every collision that creates thousands of new bullets waiting to find their target. Number 8. The Salyut 7 Toxic Tomb. On February 11, 1985, Soviet ground control lost all contact with the Salyut 7 space station. The electrical system had failed catastrophically. Batteries drained completely. Solar panels, unable to track the sun without power, went dark. The station tumbled silently in the void, 350 kilometers above Earth, transformed from humanity's orbital outpost into a frozen, lifeless hulk. For 4 months, it drifted as a tomb, its interior temperature plummeting to 20 degrees below 0 Celsius, all systems dead. On June 6, 1985, cosmonauts Vladimir Janibekov and Viktor Savinik launched aboard Soyuz T-13 on what many considered a suicide mission. Their objective: manually dock with a tumbling, powerless station and attempt repairs that had never been tried before. No crew had ever boarded a completely dead space station. On June 8th, Janibekov executed one of the most difficult dockings in space spaceflight history, matching rotation with the slowly spinning station and making contact in complete darkness. When they opened the hatch and floated inside, they entered conditions that defied human habitability. The interior was dark, silent, and bitterly cold. Frost covered every surface. Ice crystals floated in the stale air. Worse still was the overwhelming chemical smell. Toxic propellant had leaked from the station's attitude control system, contaminating the interior with unsymmetrical dimethylhydrazine and nitrogen tetroxide, both violently carcinogenic and corrosive. The cosmonauts had no choice but to work in this poisoned environment, breathing contaminated air, touching surfaces coated with frozen toxic residue. For weeks, they labored to restore power, manually orienting the entire station using their Soyuz thrusters to point the solar panels at the sun, waiting days for batteries to charge enough to begin revival procedures. They succeeded, bringing Salyut 7 back from the dead. But at what cost? Both cosmonauts were exposed to toxins that damaged liver, kidneys, and DNA itself. The long-term health effects were never fully documented. What price did they pay for proving that humans could survive where they shouldn't, working in conditions designed to kill them, all for a space station that would be abandoned just a year later? Number 7. Skylab's Uncontrolled Reentry. America's first space station, Skylab, was a monument to human achievement. 84 feet long, weighing 77 tons, launched atop the final Saturn V rocket on May 14, 1973. 3 crews lived aboard during 1973 and 1974, conducting groundbreaking research in solar astronomy, Earth observation, and long-duration spaceflight. When the last crew departed on February 8, 1974, NASA planned to leave Skylab in orbit until the space shuttle could boost it to a higher, stable orbit or retrieve it entirely. The station was expected to remain aloft until at least 1983, but the sun had other plans. In 1978 and 1979, solar activity surged beyond predictions. Solar radiation heated Earth's upper atmosphere, causing it to expand outward. At Skylab's altitude of 270 miles, atmospheric density increased dramatically. Drag accelerated. The station began losing altitude faster than any model had predicted. By early 1979, NASA faced a terrifying reality. Skylab was falling, the space shuttle wouldn't fly until 1981, and they had no way to safely control where 77 tons of metal would hit the planet. NASA attempted desperate measures, using Skylab's remaining nitrogen thrusters to adjust its orientation and timing, trying to target the re-entry to remote ocean areas. On July 11, 1979, as the world watched in collective anxiety, Skylab broke apart over the Indian Ocean and scattered debris across Western Australia. Pieces weighing over 2 tons slammed into the outback at thousands of miles per hour. Remarkably, no one was injured, but it was pure chance. The station's orbital inclination meant it passed over 75% of Earth's population on every orbit. The Skylab crisis revealed an uncomfortable truth about the space age. We had launched massive structures into orbit with no reliable plan for bringing them down safely, and our ability to predict orbital decay was dangerously inadequate when solar activity deviated from expectations. Number 6. Columbia's foam strike. On January 16, 2003 at 10:39 a.m. Eastern Time, Space Shuttle Columbia lifted off from Kennedy Space Center, carrying 7 astronauts on a 16-day science mission. 81.7 seconds into the flight, a piece of foam insulation broke away from the external tank's left bipod ramp. The debris, roughly the size of a briefcase and weighing 1.67 pounds, tumbled through the air and struck the leading edge of Columbia's left wing at a relative velocity of 545 miles per hour. Launch cameras captured the impact, but the footage wasn't reviewed until the next day. When engineers saw it, they immediately requested high-resolution satellite imagery to assess potential damage to the wing's thermal protection system. Management denied the request. Foam had shed on dozens of previous shuttle flights. It had always been treated as a maintenance issue, not a flight safety concern. The debris was so light, so seemingly harmless. How could it possibly threaten a spacecraft designed to withstand the violence of launch and the inferno of re-entry? On February 1st, 2003, Columbia began its descent toward Florida. At 207,000 feet above Texas, traveling at Mach 18, superheated plasma at 3,000 degrees Fahrenheit found the breach the foam had created in reinforced carbon-carbon panel 8. The hole was perhaps 6 to 10 inches across. Plasma poured into the wing's interior, melting aluminum structure like a blowtorch cutting through butter. The wing failed. Columbia tumbled out of control and disintegrated, killing all 7 crew members. Post-disaster testing at the Southwest Research Institute proved what management had refused to believe. Foam traveling at 545 miles per hour carried 3,000 to 4,000 foot-pounds of kinetic energy, enough to punch through the wing's leading edge with devastating force. The experiment wasn't the foam strike itself. itself. It was the normalization of deviance, the cultural acceptance of escalating risk because previous flights had survived. How many other acceptable anomalies are we ignoring right now, waiting for the precise conditions to trigger the next catastrophe? Number 5. Apollo 13's Cascade failure. On April 13, 1970, at 55 hours, 54 minutes, and 53 seconds into the Apollo 13 mission, astronaut Jack Swigert performed a routine procedure, stirring the cryogenic oxygen tanks to prevent the contents from stratifying. He flipped the switch. 200,000 miles from Earth, a spark ignited inside oxygen tank number 2. The tank exploded with enough force to rupture the service module's Bay 4, blowing a 13-foot panel into space, and crippling the spacecraft's power and life support systems. Commander Jim Lovell radioed the words that would define the crisis. "Houston, we've had a problem." But the disaster hadn't begun with that switch flip. It had been building for years, a cascade of failures across time and organizations that would converge in a single catastrophic moment. In 1965, oxygen tank number 2 was manufactured for Apollo 10. In 1967, spacecraft power specifications changed from 28 volts to 65 volts. The thermostat switches in the tanks were upgraded to handle the higher voltage, except tank number 2's thermostats weren't upgraded. They remained 28-volt components in a 65-volt system. In March 1970, during pre-flight testing, the tank was dropped approximately 2 inches during installation, jarring loose the fill tube. When ground crews tried to empty the tank, it wouldn't drain normally. Someone made a decision: use the tank's internal heaters to boil off the oxygen. For 8 hours, the heater ran continuously. The thermostat, designed to open at 80 degrees Fahrenheit and prevent overheating, tried to do its job. But with 65 volts flowing through a 28-volt switch, it welded itself shut from the overcurrent. Temperature inside the tank soared past 1,000 degrees Fahrenheit, incinerating the Teflon insulation on the electrical wiring. Nobody knew. The welded thermostat couldn't signal the overtemperature condition. Weeks later, in the vacuum of space, that damaged insulation allowed bare wires to arc in a pure oxygen environment pressurized to over 1,000 pounds per square inch. The result was instantaneous and catastrophic. Apollo 13 demonstrated that spaceflight operates on such narrow margins that a cascade of seemingly minor errors, separated by years and invisible to inspection, can combine with perfect precision to create disaster. Number 4, the Vela incident double flash. On September 22nd, 1979, 0053 Greenwich Mean Time, a United States Vela satellite orbiting 110,000 kilometers above Earth detected something that should not exist. The satellite's bang-emitter sensors, designed specifically to identify nuclear detonations from space, registered a characteristic double flash of light over the remote southern Indian Ocean. Approximately 47 degrees south latitude, 40 degrees east longitude. The signal was unmistakable, a brilliant initial flash, a brief dimming period as the fireball cooled, then a second brightening as the expanding plasma became transparent to its own radiation. It was the optical signature of a nuclear explosion, estimated yield 2 to 3 kilotons. The Vela satellites had detected 41 previous confirmed nuclear tests with perfect accuracy and 0 false positives, but no nation claimed responsibility for this detonation. It had occurred in one of the most remote regions on Earth, far from any acknowledged test site, during a period when atmospheric and underwater nuclear testing had been banned by international treaties since 1963. The White House convened an expert panel led by Dr. Jack Ruina. Their investigation found no corroborating evidence, no seismic signals, no radioactive fallout detected by aircraft patrols, no hydroacoustic confirmation from Navy listening arrays. The panel's conclusion was inconclusive, suggesting the signal might have been caused by a meteoroid striking the satellite itself, but scientists criticized this explanation as statistically improbable. The double flash timing was too precise, too perfectly matched to nuclear detonation physics. Intelligence analysts believed otherwise. Evidence pointed to a joint nuclear test by Israel and South Africa, two nations known to have covert nuclear weapons programs and documented military cooperation. Some researchers detected an ionospheric disturbance consistent with electromagnetic pulse effects. Others identified possible hydroacoustic signals that had been dismissed or misinterpreted. More than 4 decades later, the US government has never officially confirmed what caused the Vela incident. If it was a nuclear test, it means weapons were detonated in violation of international law, and the world's most sophisticated detection system witnessed it but couldn't, or wouldn't, definitively identify who was responsible. What other covert experiments might be hidden in the vast, unmonitored spaces of our planet, their evidence detected but deliberately left unexplained? Number 3. Kosmos 954's radioactive rain. On January 24, 1978, at approximately 6:53 Universal Time, a Soviet nuclear-powered reconnaissance satellite designated Kosmos 954 re-entered Earth's atmosphere over northern Canada. This wasn't supposed to happen. The satellite's BES-5 reactor, containing roughly 50 kilograms of highly enriched uranium-235, was designed with a safety system. When the satellite reached the end of its operational life, the reactor core would separate and boost itself to a disposal orbit 900 to 1,000 kilometers above Earth, where it would remain radioactive but safely distant for centuries. The system failed completely. Instead of separating, the reactor core remained detached as the satellite plummeted through the atmosphere, breaking apart and scattering debris across 124,000 square kilometers of the Northwest Territories. The debris field stretched from Great Slave Lake across the tundra, a swath of radioactive contamination nearly 500 kilometers long. Operation Morning Light, a joint Canadian-U.S. recovery effort, deployed over 100 personnel equipped with radiation detectors. Helicopters and ground teams conducted systematic searches through sub-zero temperatures. They recovered approximately 65 kilograms of debris, including fragments emitting radiation levels up to 200 roentgens per hour, lethal doses for unprotected humans. The largest piece was a 5-kilogram section of the reactor core found near Rolina, but 65 kilograms represented less than 1% of the satellite's mass. The rest was never found, vaporized during re-entry, buried under snow and ice, or sunk through frozen lakes. The cleanup cost 14 million Canadian dollars. The Soviet Union eventually paid $3 million in settlement, but the financial cost was trivial compared to the revelation. Orbital nuclear reactors could fail catastrophically, contaminating vast territories with weapons-grade uranium that will remain radioactive for millennia. Even more disturbing, approximately 50 Soviet reactor cores remain in those so-called disposal orbits, each containing uranium fuel, each one gradually losing altitude, each a potential radioactive satellite waiting for orbital decay to bring it home. Number 2. The Nedelin Catastrophe. On October 24, 1960, at approximately 6:45 p.m. local time, over 200 Soviet military personnel, engineers, and scientists gathered around a fully fueled R-16 intercontinental ballistic missile at Site 41 of the Baikonur Cosmodrome in Kazakhstan. The rocket stood vertical on the launch pad, its tanks loaded with 125 tons of hypergolic propellants, unsymmetrical dimethylhydrazine, and nitric acid, chemicals so reactive they ignite spontaneously on contact. Political pressure to demonstrate the new weapon before the anniversary of the Bolshevik Revolution had compressed the test schedule. Safety protocols were abandoned. Personnel worked directly beside the fueled rocket. Marshal Mitrofan Nedelin, chief of the Strategic Rocket Forces and the man responsible for the Soviet Union's missile program, reportedly sat in a chair near the base of the rocket smoking a cigarette. At 6:45, an electrical signal erroneously activated the second stage engines while the first stage remained fully fueled. The second stage exhaust sprayed downward onto the first stage propellant tanks. They ruptured instantly. 125 tons of hypergolic fuel mixed and ignited, creating a fireball that exceeded 3,000 degrees Celsius. The launch pad became an inferno. Personnel within 100 meters were incinerated instantly. Many vaporized so completely they left nothing identifiable behind. Those farther away tried to run but were caught by the expanding flames. The propellants burned with such intensity that metal structures melted. Bodies were reduced to ash and shadows. The official death toll, released only after the Soviet Union collapsed, listed 126 confirmed dead. The true number may have exceeded 200. The Soviet government buried the disaster under total classification. Families were told their loved ones had died in unrelated accidents, airplane crashes, or illnesses. Death certificates were falsified with different dates and locations. The West knew something catastrophic had occurred, but learned the full horror only in 1989, nearly 30 years later. What other disasters might still be hidden in the classified archives of nations racing toward technological supremacy, their victims erased from history to preserve the illusion of infallibility? Number 1. Starfish Prime, the day we nuked space. On July 9, 1962, at 090009 Universal Time, the United States detonated a 1.4 megaton thermonuclear weapon 250 miles above the Pacific Ocean. The weapon, a W-49 warhead carried aloft by a Thor rocket launched from Johnston Atoll, was part of Operation Fishbowl, a series of high-altitude nuclear tests designed to understand how how nuclear weapons behaved in space and whether they could be used to destroy incoming Soviet missiles. What happened next exceeded every prediction and fundamentally altered Earth's orbital environment. The detonation created an artificial aurora visible from Hawaii, 900 miles away. The sky lit up with colors that lasted 7 minutes as charged particles spiraled along Earth's magnetic field lines. But the visual spectacle was the least of the consequences. The blast generated an electromagnetic pulse that propagated across the Pacific, knocking out streetlights in Oahu, damaging electrical systems, and demonstrating that a single high-altitude nuclear explosion could cripple infrastructure across thousands of square miles. More catastrophic was what happened in the magnetosphere. The explosion injected an estimated 10 to the 30th power electrons into the Van Allen radiation belts, creating artificial radiation zones that increased background radiation levels by factors of several thousand. These trapped particles immediately began damaging satellites. Within months, approximately 1/3 of all satellites in low Earth orbit had failed or been destroyed, including Telstar 1, the world's first commercial communications satellite, and the United Kingdom's Ariel 1, the first international satellite. The radiation effects persisted for years, gradually decaying but continuing to threaten spacecraft and astronauts. Scientists, including Dr. James Van Allen himself, expressed alarm. The experiment had contaminated the very region of space Van Allen had discovered just 4 years earlier. We had weaponized the magnetosphere, turning Earth's protective radiation belts into a hazard zone. The test proved that nuclear weapons could be devastating in space, not through direct blast effects, but through electromagnetic pulse and long-duration radiation that could sterilize entire orbital zones. We had tested whether we could make space itself uninhabitable. The experiment succeeded, and we've been living with the consequences ever since. If you want to see more videos like this, click the video on screen now and make sure to subscribe.